Now I think the mic is on because that echoed. Very good. Okay, great. Thank you. So I'm imitating Kyle's approach of having some pictures as slides, though sadly a little bit fewer. So I want to start out with the satellite construction, which I'm mostly defining by picture, that features construction, not constructure, but to a pattern knot, which I'm going to call a knot in the solid torus, and to a knot in S3, which by considering a tubular neighborhood of it, we can think about as a map of the solid torus into S3. We associate the satellite knot P of K. And in this notation, I always have to focus on the composition. It is, in fact, K composed with P. And I should say now that all of my manifolds today are smooth and they're oriented. And if I write it as a product, I really mean that it's parameterized as a product, not just diffeomorphic to a product. If you're curious about non-smooth things, I would be delighted to talk about it after the talk. Okay, so we have this satellite construction illustrated here, pattern companion knot that is used in the literature sometimes, and the satellite knot. And this is almost surely most famous for the trichotomy of knots that says that every knot is either a torus knot or a hyperbolic knot or a satellite knot. So I guess you need some conditions sort of ensuring that P and K are non-trivial for something to truly be a satellite knot in that sense, as we'll see later. But okay, satellites are going to play a fundamental role for us, and I'll say more about that momentarily. But the other key definition I want to give, or remind you of variously, is of concordance, an equivalence relation on knots in S3. So we say that two knots, K0 and K1, are, again, smoothly concordant, right? If they co-bound an embedded annulus in S3 cross I. So here we're really thinking about K0 is living in S3 cross 0, K1 is living in S3 cross 1, and there's a smoothly embedded annulus between them, but it's you know, the annulus itself is homomorphic to S1 cross I, but it's almost surely not embedded in a level preserving way. That's the whole interesting thing that happens here. So are concordant if they co-bound an annulus. Fantastic. And so broadly speaking, I think something very interesting is to ask about the interaction of satellites in concordance. I should say, sort of before I really get going on this, that one of the major ways the satellite construction shows up in concordance is really as an extremely powerful and flexible way of building examples of knots that have certain properties, or by sort of different Kirby diagram shenanigans, manifolds that have certain properties. I'm not really going to go into that today. Instead, I want to say, well, we have this definition. I said it's an equivalence relation. And so if I write below here, is this legible, or should I go to the next board? Back of the room. You're happy? Great. I won't go any lower than this, but unhappy? Happy. Okay. The collection of knots in S3, modulo smooth concordance, I'm always going to call C for concordance. And the big picture question of a lot of what I find interesting is what kinds of functions do we get from satellites? And implicit in this is that we do get well-defined functions on C. So why is that, by the way? They do exist. So what do I need to show? I need to show that for any pattern P and for any K0 and K1, if K0 and K1 are concordant, then P of K0 and P of K1 are concordant. And in fact, it's sort of a one line. If they start with our concordant knots, by definition, they co-bound an annulus. I'm just going to say between K0 and K1. And I can take a tubular neighborhood of that annulus. And I can think of a tubular neighborhood of that annulus as being S1 cross D2 cross I, writing the cross D2 in a different place than perhaps you want me to, but fine. And the reason I'm writing it that way is I can think about P cross I living in there. And so that P cross I is an S1 cross I, it's itself an annulus. And you can check that P cross I is an annulus, well, between P of K0 and P of K1. So actually, we don't need to put any conditions on our patterns. No matter what, we get a well-defined function on C. And I think I should pause here because these are the major players. And if you have a question, it would be an excellent time to ask it. Very good. Okay. So this is a relatively general question. A number of people have done work on it, but I want to be more specific. And in particular, an observation dating back almost 60 years to Fox and Milner is that this isn't just a set, it's a group. C is a group with, okay, how do I add with respect to two concordance classes of knots? Well, as you can see by the fact that I made that mistake, we're just going to take their connected sum. Okay, so a question that remains extremely open is what group is this? It's abelian because connect sum is an abelian operation just on knots. It's countable because there are only countably many knots to begin with. There exists a lot of two torsion elements, a z mod 2z to the infinity. There exist a lot of infinite order elements, z to the infinity. As far as purely group theoretic properties goes, that is a complete list of what we know. In particular, it remains entirely open if there's any torsion besides two torsion. Could be, but who can say? Or if, for example, is there a copy of the rationals living inside of C? Presumably not, but wide open. Okay, but now that we have that this is a group, I think it's reasonably natural to ask, in particular, our refined question, I guess, is when is, and I apologize, this is slightly unkind of me, I'm going to call the map from C to C induced by a pattern P still just P. If it causes confusion at any point, complain, ask me. So when is the induced map from P a homomorphism? The motivation behind this is essentially we would really like there to be some interesting homomorphism defined by satellite constructions. We know some things about the existence of interesting satellite maps, that they can be bijective, that there's a certain class of them that conjecturally induce sort of a fractal structure on knot concordance with respect to some reasonably nice geometrically defined metric. But do they respect the group structure? And so that's sort of what we're going to focus in on now. But I'm going to erase this first. Answer to the question, at least partial, is sometimes. In particular, let me draw you some examples of pattern knots that do induce homomorphisms of the smooth concordance group. Okay, well, first of all, we could take this pattern. And this induces, again, even three-dimensionally, the identity map, which is undoubtedly a homomorphism. We could sort of similarly, uninterestingly, take that to be our pattern. And no matter what knot you tie the solid torus in, you just get the unknot. So this is the 0 map. And there is one other that's really different from these two. which is the arrow goes the other way, i.e. the map induced here is reversal. The fact that there are knots that are not concordant to their reverses, i.e. that this map is not the same as this map, is first due to Livingston. It takes some effort, but it is true. So we have at least 3 maps, and I guess opinions can vary about how interesting they are. And I should note, there's a notion of concordance of patterns. So if I took another pattern, which was concordant to, for example, this in the solid torus cross I, it would induce the same map on concordance. And so you can certainly get these maps in other ways. If you want an example of that, if you know the Maser pattern, if you don't, you'll see it momentarily. If you know the Maser pattern, but you make it alternating, that's concordant to the core. And so it also induces the identity. So we don't really want to, I mean, those don't give you interesting maps, even if they are somehow not quite the same satellite operator. As far as we know, this is it. And so Hedden's conjecture, which he seems to have made at a couple conferences in 2016, though not really in any published literature, is that the only group homomorphisms induced by satelliting are the ones I've already written down. Identity, 0, and reversal. So this is a sad conjecture, if true. Yeah. Okay. Yes. So that is a great, I think, very hard open question. So just to repeat that, could you get the identity map from a pattern that is not concordant to the core in the solid torus? So in general, the question of whether 2 patterns that are not concordant patterns can induce the same map on concordance is totally open in the smooth category. In the topological category, interestingly, it's not open. So for example, the Whitehead pattern, which you will also see in a moment if you don't know what it is, the Whitehead pattern is not concordant to the 0 pattern. However, the Whitehead pattern applied to any knot is topologically slice. So in that specific case, we see examples of patterns that are different but induce the same map on topological concordance. But as far as we know, that only can happen, we only see examples of that happening, rather, in the winding number 0, and I'm also going to say what winding number is, topological setting, where things are just sort of weird and bad. Other questions? Yes. Great question. This is not true in the algebraic concordance group. And in fact, it makes it kind of hard. In fact, let me just sort of make as a remark, what's the first thing you should want to be true for a homomorphism? What's the first thing that's true for a homomorphism? It sends the identity to the identity. If P of U is concordant to U, then P induces a homomorphism on the algebraic concordance group. So somehow this is maybe it's quite false, but maybe that's a little bit of a lie in the sense that there's only one such map for each winding number. And so you don't get that many interesting things. You know exactly what they are, but you do get more for sure. If you don't know what the algebraic concordance group is, I will say it's a quotient of the concordance group that you can actually compute. And if you look at higher dimensional definitions of concordance of, let's say, S3s and S5, they're isomorphic, but in the classical setting, they are known to not be isomorphic. Great question. Any others? Okay. So I promised you a partial resolution of Hedden's conjecture. And before I can tell you sort of what that is, I need to either tell you or remind you of the winding number of a pattern, which I'm going to do mostly by looking at these pictures. The winding number of a pattern tells you how many times it wraps around the solid torus counted with sine. So I promised you, if you haven't seen them before, we have the Whitehead pattern here. It's winding number 0, though it's, whenever I say winding number, you can implicitly insert algebraic if it makes you happy. It's not geometric winding number 0. We have the maser here, we have the 2-1 cable, and then we have our old familiar, not so interesting friends below. And in particular, it's not so hard to show that if you have two patterns with different winding numbers, there's no way they can induce the same map on concordance. So in particular, if true, then it would be true. This is a weaker statement, but whenever the winding number of P is greater than 1, P does not induce a homomorphism. So this is the sort of sense in which it's quite striking how much we don't know. In general, one can say that the behavior of satellite operators is coarsely determined by their winding number, and you can make that precise in various ways. And so Hedden's conjecture is predicting that for large winding number, none of them ever induce homomorphisms, but we can't show that, even though sort of all of, anyway, a consequence. And this is the thing where we didn't prove this. We proved a slightly weaker version of this. So let me write that down for you. And this is joint work with Randall Johannesmeyer and Hilary Kim. From the preprint is summer 23. Okay, so it's sort of partial resolution to this part. So if the winding number of P is even and not divisible by 8, okay, then P does not induce a homomorphism, but in fact something a little bit stronger is true. Then there is a knot K such that P of minus K is not concordant to minus P of K. And here minus denotes the inverse in the concordance group, which is the mirror reverse. Yes. I should have said possibly earlier, okay, more sort of evidence in favor of Hedden's conjecture is we don't have any interesting examples of patterns that ever behave in a homomorphism-like way, even for sort of two knots K1 and K2, having P of K1 connect some to K2 be concordant to P of K1 connect some P of K2. The only way we can get that is, well, okay, these very boring examples, or when at least one of those things is concordant to the knot. So sort of cheating. And so this is the theorem that I would like to spend the rest of the time telling you about, the ingredients that go into the proof. Any questions before I do so? So I should say the even condition is really, really crucial. In particular, this sentence is not true for P odd. There exist patterns of odd winding number with the property that P of minus K is always concordant to minus P of K. They don't seem to be homomorphisms, but they at least satisfy this weaker property. Again, the non-zeroness is also certainly a necessary property since we have the zero map. But you might well wonder what's up with divisible by 8. And we might see a little bit more about that later. I don't have a satisfying answer. It comes out of the obstructions we use. They fail in the divisible by 8 case. And that will make a lot more sense once I tell you about the obstructions. One hopes. Okay, so the key, there's a whole zoo of concordance obstructions in the world. What's the one we use? So our key fact is, so we want to obstruct this. Well, okay, i.e. P of minus K connects some P of K is not concordant to the unknot. So we want to, if you've heard the language of a knot being sliced, we want to show that P of K connects some P of minus K is not sliced for some K. And we have total flexibility in which K we choose, and we're definitely going to use that. But the key obstruction we use that is if, let me just say J is slice and N is a prime power, then the n-fold cyclic branched cover of S3 along J bounds a rational homology ball. And let me emphasize, so far you might well ask, where have you used smooth? And so far, I guess, well, we don't prove this theorem in the smooth category. Why don't we prove this theorem in the smooth category? Because in particular, if we look at the minimal D invariant of the branched cover, so to a rational homology sphere, which all of these prime power branched covers are, and a spin C structure, we have this Heegard floor D invariant, which is a rational number. Okay, in general, you have to pick a spin C structure. However, I think I need one more parentheses. For a rational homology sphere, which this is, there are only finitely many spin C structures. And so you can look at all of the D invariants and pick the smallest one. And so I want to say that the smallest D invariant is no more than 0. This is a weird thing to write. This is not how this is usually written. What is usually written is that there is a collection of spin C structures for which the corresponding D invariants must vanish. But we didn't want to keep track of spin C structures, and we didn't have to keep track of spin C structures. So instead, we will just work with whatever the smallest D invariant one is. So this, just to emphasize, is true if this is smooth and this is known to be smooth if J is smoothly sliced, i.e. smoothly concordant to the unknown. So that's why this talk is all in the smooth category. So that's what we're going to show, is that if the winding number is even and not divisible by 8, then in fact there's a power of 2 for which the D invariant of sigma n of P of, oh, this should be a J, shouldn't it? Sigma n of P of K connects some P of minus K is not less than or equal to 0. In fact, it's as large as we want it to be. Okay. So our goal, I think I have one more line. Our sort of subsidiary goal is to understand the D invariance, well, of branch covers interact nicely with connected sums. So understand the D invariance of sigma n P of K connect sum sigma n P of minus, oh, I'm always losing parentheses here. So our goal is to understand the D invariance of branch covers of connected sums of branch covers of satellite knots. And so in particular, we want to understand the D invariance of satellite knots. Sorry, the branch covers of satellite knots. Let me erase this. Wonderful. So when we have, the way I defined patterns was thinking of them as knots in solid tori. So for example, we had our friend, the Whitehead pattern, who looks something like this. And I'm just going to draw this meridional curve to n. I'm always going to call this eta. Here's my pattern P. You can equally well think about a pattern as being a two-component link, where one of the components is specified and is forced to be the unknot. Let me put orientations on this since I promised I would. One of the components is specified in the unknot. In particular, so observation, if n divides the winding number of P, then this curve eta lifts to the branch fold cover of S3 along P of U. And what I mean by lifts is to n distinct curves. this is a good exercise in covering spaces / winding numbers if you want something to do with the next few minutes. Okay, so if we have this divisibility condition, then we can lift eta to a collection of curves in the branch cover of P of U. And this is a really important decomposition. Just doing this for no reason. If I want to gate the n-fold cyclic branch cover of P of K for any K, what I do is I take this 3 manifold I start with, I drill out a neighborhood of all of my lifts, and then I stick in a bunch of copies of the exterior. By the way, decompositions like this exist when n doesn't divide the winding number. You have fewer lifts, so you're cutting out fewer curves. And instead of gluing in copies of the exterior of K, you're gluing in copies of cyclic covers of the exterior of K. But okay, so this is what we want. Okay, so this somehow is going to be the crucial thing. In particular, this 3-manifold link pair, sigma n P of U and these eta curves, sort of encodes the structure of all of the branch covers sigma n P of K across all K in a nice way that will be really useful to us. And so now, I guess I should erase for space reasons. Yeah, okay. And so now I want to tell you a result that is going to give us some information on this piece using information coming from this manifold and this link. And this is joint work with Ty Lidman and Juanita Pinzon Caicedo. So, and I'm going to state a slightly special case. You can ask me about why it's slightly special later if you want, just because it's a little bit shorter. So let's suppose we have a power of 2 that divides the winding number of P. And then here's the condition. Well, I have these curves, eta I tilde and eta j tilde. They're disjoint, simple closed curves in a rational homology sphere, sigma n P of U. There exists a generalization of the linking number in S3 that we know and love to arbitrary rational homology spheres. It's now rationally valued instead of integrally valued. If you're familiar with the Q mod Z linking form on the first homology of a rational homology sphere, it's a Q-valued lift of that. I can say more if you want me to. But for now, this is in Q. It's an integer if, say, either of these curves is homologous. That's all you need to know. So if this linking number satisfies 2 conditions, really. So first of all, it's greater than or equal to 0 for all distinct I and j. It doesn't really make sense for I equals j, but if it's greater than or equal to 0 for all I not equal to j, but it's not identically 0, well, then there is a non K such that P of K, P of minus K is not concordant to minus P of K. And the way we do that is by looking at D invariance of branch covers, as I've hinted at. And in fact, I want to tell you a little bit more about the proof of this theorem, how we sort of leverage this linking number condition to get control on the D invariance of these composite things. But any questions before I do that? So I'm going to give Really sort of dooming myself here by only using half the board all the time. Okay, so the proof idea, I'm going to give you a proof sketch for this. When the branch cover of P of U is just S3. It allows me to skip a step. Many interesting examples have this property when P of U is unknotted. Yeah, and it just makes life a little bit easier. So what we want to do is, again, get control of the D invariance of sigma and of P of K and P of minus K sort of simultaneously. And I am going to continue to erase. Actually, don't think I can avoid it here. So let me get this right. So what we're going to do is we're going to think about, well, this is, remember, just S3, and our link consisting of the n distinct lifts of eta. And our linking number condition here of being greater than or equal to 0 always, but not identically 0, is actually exactly going to tell us that there's a negative definite cobordism, well, from this pair to still S3 and some other link, where I'm going to specify the linking numbers of this link, where the linking number of Li Lj equals 1 if I and j are 1 and 2, and 0 else. Okay, so this is not too bad. It sort of purely applies a very simple negative definite cobordism. But why is this useful to us? If we switch now and think about these sort of vertical arrows are gluing in, well, like cutting out the link and then gluing in a bunch of copies of the exterior of K. There you should sort of be a little bit suspicious that I'm sweeping under the rug how I glue in these things. You do have to keep track of that. I'm not going to talk about it. So okay, if we glue in a bunch of copies of the exterior of K in the right way, then I already said this gets us sigma n P of K. And this gets us something else. It's probably not a branched cover. It's in fact definitely not a branched cover of anything, because we've sort of, I didn't say this before, but these linking numbers, this link has a symmetry coming from the action of the covering transformation. And we have profoundly broken that symmetry by making the linking of sort of two specified components be 1 and everything else be 0. So this I'm just going to call, do I have a good name for it or a bad name for it? I have a bad name for it. Why? Okay, fine. And one of the most fundamental nice things about D invariance, and I'll just use D min again, is that this tells us that the D invariant of this thing is greater than or equal to the minimal D invariant of Y. They behave predictably under negative definite cobordisms. So okay, remember vaguely we're going to make this large at the end of the day. We're going to make the minimum D invariant of sigma n P of K plus the minimal D invariant of sigma n P of minus K very large. And we already have it greater than or equal to something. But we don't really know what that something is, except that it's sort of obtained from this link in S3. But now we're going to apply a result of Matveyev. And let me just sort of write something first and then tell you what I mean by it. Get this orientation right, since it certainly matters. Okay, so first of all, I just want to say this link here is a hop link. You need an unlink. It has the same linking numbers as this. That's exactly what we were aiming for. A theorem of Matveyev says that any two links with the same pairwise linking numbers are related by a sequence of clasper surgeries, which you can think about as grabbing each of the link, grabbing one link in 3 different places, however you like, with many strands, grabbing the link in 3 different places and tying the Borromean rings into it. So Matveyev says any two links with the same pairwise linking number are related by these surgeries. Surgeries is maybe highly in quotes there. But what this, I'm just going to say a little bit vaguely, is that this, and this is a good chunk of the technical work of the paper, this is bounded complexity with respect to D invariance. In particular, the fact that we're working here with this link in S3 that only depends on the pattern tells us that no matter what K is, so let me maybe just put YK for emphasis here. This manifold definitely depends on K once we've glued in all the exteriors of K. The minimal D invariant of YK is going to be, well, it's going to be not so different from the D invariant of whatever we get when we glue in a bunch of copies of the exterior of K into here. In particular, there's going to be some constant that only depends on the pattern, not on K, such that the minimal D invariant of YK, well, okay, I haven't told you the framings, but if I did, it would be a mean pop quiz question to ask you what this manifold is. It turns out sort of none of these really end up contributing. You actually get the twofold branched cover of the 2-1 cable of K, which actually has another nice name. It's +1 surgery on K connects some K reverse. This is something that for many cases, and again, we have a lot of control over K here, we can understand, and therefore, by jacking this D invariant up sufficiently, we can make sure that CP doesn't matter, canceled out. And so let me write a little bit about that, at least, just to wrap this up. So what do I want to say? Great. I want to say choose K in terms of P such that the D invariant of K connects some 1 surgery on K connects some K reverse is quite large. And if we do the same thing for minus K, it's just 0. Because then we'll have the connected sum of these 3 manifolds, i.e. the n-fold cyclic branch cover of P of K connects some P of minus K is positive. It doesn't have the vanishing D invariant property. So that is the end of the sketch of this proof. When sigma n P of u is not unknotted, there's an extra step at the beginning, and it's another sort of bounded complexity move. Okay, actually, sorry, that's a little bit of a lie. When sigma n P of u is not S3, but your curves, your eta curves are still null homologous, then it's just another step at the beginning, not this step, a different bounded complexity kind of step. When your curves aren't null homologous, you have to use it. You have to first prove the theorem in the case when they are null homologous, and then use a cheap trick that you are welcome to ask me about later to extend it to the arbitrary setting. Okay, so that is the sketch of our obstruction. And so in particular, let me now tell you, we're now in a good place to talk about the proof idea for if the winding number of P is even but not divisible by 8, not a homomorphism, and it's probably quite clear at this point, it's going to factor through this obstruction. We need to show that there's some power of 2 dividing the winding number for which this linking number non-negativity is satisfied. Okay, and in fact, there's sort of 2 cases here. There's equivalent to 2 mod 4 and equivalent to 4 mod 8. Let's say and then if you want to ask me about the 4 mod 8 case, I would be very happy to talk about that afterwards. Okay, so in this case, we take n equals 2. The only thing we know divides the winding number. And it's a particularly nice setting, because remember our condition is that if we take any two distinct lifts, their linking number is greater than or equal to 0, but not identically 0. In this case, there's only two lifts. And so it's either greater than or equal to 0. Sorry, it's either greater than 0 or less than 0. And it turns out if it's less than 0, we can apply a cheap trick to get a related pattern for which it's greater than 0. So what I want to say for you is it suffices to show that the linking number in the branch double cover of P of U of the two different lifts is not 0. That's all you have. You only have to worry about one linking number. Okay, so how does this argument go? In fact, this argument is essentially a parity argument. The reason that this linking number is never 0 in this case is because it's odd. The reason I was a little bit hesitant there in saying odd is that it is a rational number, but it turns out you can have a good notion of oddness of rational numbers. And it's an odd rational number, and 0 is not an odd rational number. I will be more precise about what I mean by that. Okay. Any questions before I erase this? Okay. Our sort of prototypical example that actually is going to sort of be a useful computational tool for us, and I'm just going to draw it for 1n and then stop, okay, is the N1 cable. So here, this is my P of U, and then that's my eta curve. 1, 2, 3, 4, 5. Okay, 6 is equivalent to 2 mod 4, and I drew the right thing. So let me compute it in this specific case for you all, the linking number in the double branch cover. So the first thing I want to do is a cheap trick for anyone who's taking notes. It's to say that this two-component link is symmetric. And so I can equally well, think of it as P of U and eta. In particular, okay, P of U is certainly unknotted. And if I take the branch double cover along P of U, which I want to think about as cutting S3 open along this disk and then regluing two copies, what I get, that's the right dashed line to draw. What have I done? 1, 2, 3, 4, 5. Here. And similarly, down here. So this is, in fact, a picture of which one of them I call eta 1 tilde and eta 2 tilde is totally arbitrary. And eta 2 tilde in sigma 2 of P of U, which is indeed S3. Okay, this is a link we know and possibly love. It's the 2, 6, or 6. I guess in this picture it's the 6, 2 torus link. But if you think about it as the 2, 6 torus link, it, at least to me, makes it slightly clearer that in this case, the linking number is 3. And a very, very similar picture tells us that, maybe I'll just write this in a different color, for C2N1, an analog of this, the linking, let me just write C21 of U, which is the unknot. So this is S3. It's a boring linking number. It's a boring 3 manifold. Is just N. And and I'm being very bad in my letters. Let's call it M. 2m1 cable. The linking number there is m. And so in particular, whenever 2m is equivalent to 2 mod 4, this is odd. Okay. This is not very exciting. I mean, this is giving you a proof that the 2m1 cable does not induce a homomorphism for m odd, but we already knew that. So, okay, how does the rest of the proof go? It actually goes by relating it to this, which is also part of why I wrote it. In general, a winding number, let me just stick with this, 2m pattern, P, can be converted to the 2m1 cable by crossing changes. The two curves in the solid torus are a topic. And you can think about accomplishing these crossing changes by doing surgery on certain curves. You can lift these curves to the double-branched cover, and then you can analyze how the rational linking number changes. And that sort of heavily uses a formula of Cha and Co. And so let me say lift surgery curves to double-branched cover, and you can compute that the linking number of the thing we're interested in, so double-branched cover P of U of our eta 1, I'm going to put the P there to remind you that it's P's eta, not C's, not the 2-1 cable's eta. So let me maybe throw those in here as well, just to remind you. Well, it's not, certainly not generally equal to this. You get lots of different linking numbers, but it differs from this, right? Just going to write S3 to be more efficient. C. M plus 2 times some integer over the order of the first homology of E of U. And actually, this means we've won. Why? M is odd, since we were taking a pattern whose winding number is equivalent to 2 mod 4. We have a 2 here, and the order of the double branch cover of a knot is itself always odd. So this expression cannot be 0. The linking number, whatever it is, it may be positive, it may be negative, but it's not 0. It's sort of a quote unquote odd rational number. And so that's how the argument goes when the winding number is equivalent to 2 mod 4. So let me briefly say something about equivalent to 4 mod 8. And also then briefly, what goes wrong? Why did I need this not divisible by 8 condition? Why can't I keep going indefinitely? But first, are there any questions about this? I'll erase. Interrupt me if there are. So in this case, we actually have to look at 2 different covers potentially, both the 2-fold and the 4-fold. So there's really 2 cases here. The first case is basically the 2-fold branched cover works. So the linking here is not equal to 0. A similar argument to this shows that it's even, but the happy fact is there are many even non-zero rational numbers. So this happens sometimes, certainly. The second case, of course, is the double branch cover obstruction fails. So we know, and we're going to use this, which is why I'm bothering to write it, that this is 0. Okay. So now though, because our winding number is equivalent to 4 mod 8, we can look at the fourfold branch cover. 4 divides the winding number for the first time. And so now we show two things. The first thing is that some of our linking numbers, and I'm just going to write sigma 4, of eta 1 tilde and eta 2 tilde. And here I am picking an implicit ordering using the action of the group of covering transformations. Turns out that it must be true that these two linking numbers also vanish. And this is sort of a geometric argument. In particular, we're sort of in our winning case again, where there's only one linking number left, sort of by the symmetries of the situation. We just need to show that the linking number in the four-failed branch cover of eta 1 tilde, eta 3 tilde, that this is not 0. And again, this holds by a parity argument, essentially the same as what we did here, but higher covers. So you might well ask, why not keep going? Why not, if you have a winding number 8 pattern, can you not look at the 2, 4, and 8-fold covers and show that one of the linking number conditions must be satisfied? The first reason is because it's just not true. There exists a winding number 8 pattern for which, let's see, the linking numbers at the 2-fold branch cover are identically 0. There's only one, so that's not hard. The linking numbers at the 4-fold branch cover are identically 0. And the linking numbers at the 8-fold branch cover are of mixed sign. So that sort of is where we can't use this result with Lidman and Pinzon-Caicedo anymore. Mixed sign, we can't draw any conclusions. And I will say roughly what goes wrong is this is sort of still true. There's still something that we can say is non-zero for parity reasons. But instead of being able to say that the other linking numbers must be 0 when we're forced to this case, we get that some sum of linking numbers must be 0. And unfortunately, things can sum to 0 while being of opposite sign. And so really, if you wanted to try and improve this, to, for example, say something about patterns of even non-zero winding number, what you need to do is improve the obstruction result with Lidman and Pinzon-Caicedo, weaken the conditions on the linking number to something like, I don't know, the sum of all the linking numbers may be appropriately weighted is non-zero. If you could prove something like that, you'd be in business. But as it is, this weird winding number 8 example just proves that you can't, you need something more. All right, I'll end my talk there. Thank you very much. Yeah, I'm thinking about T sends eta 1 to eta 2, eta 2 to eta 3, and so on.
1, 3.
Yes. So yeah, this is really these three. They're only actually these two must be equal for different symmetry reasons. Sort of rotating backwards and forwards are the same. So they are sort of, there's only sort of two possibly different fourfold branch cover linking numbers to look at. And another way of saying what goes wrong at the 8-fold cover level is that there's 4 of them all of a sudden, which is a little bit more than you want.
If the 1, 3 guy is negative, then
Yes, you use that trick again as well to show that it doesn't matter, that you only need to use everything else is 0, and so you can reflect and get positivity. Yeah, good question. Others? It depends on what you mean by easy is a little bit of a cop-out answer. I actually don't have a great reference for the literature on that. I think the first time that I definitely know it's written down is in one of Casson and Gordon's papers, but I think it was almost surely known. I mean, yeah, known significantly before then. If you want to see a proof of it, one of my favorite sources for it is Chuck Livingston and Swati Naik's. They have a draft book findable online, Introduction to Knot Concordance, and it does a lot of things very nicely. And one of them is a proof of that.